Brave as it could be, but we're fine.
You expecting anyone else?
Is Arushi around?
I haven't seen you. No. All right, if you're ready.
Yeah, fantastic.
Awesome, cool. Yeah, so today we have Tanner telling us about some direct detection stuff. Please take it away.
Yeah, everyone, thank you for having me. It's great to come in from Fermilab. That's my drive down from Logan Square by a little bit, by about 20 minutes or so. So that's a nice way to start the day. Yeah, today I'm going to talk about direct detection with magnons. We'll talk about what magnons are in more detail, but really the goal here is to find new ways to search for light dark matter candidates with low threshold experiments. And magnons are one type of excitation in targets which exist at energies much smaller than the EV scale that are being currently used with electron-based experiments. And this work is based on previous collaboration with people at Berkeley and Caltech back all the way in 2019. And then more recently with other collaborators at Caltech, and then I've been very interested in this recently, as you see by the 2504.xxx on a few different papers.
Extremely
So
optimistic.
it could be extremely optimistic, could be very busy. If Asher is listening, hopefully we can get one of these out on the archive tomorrow.
Yeah.
So, we're
I will put an X in the.
yeah, exactly. So very excited about this topic and happy to be talking about it with you all here today. So we're going to begin with a brief outline. We're going to talk about where we're at with direct detection today, just on a broad scale, because there have actually been really interesting developments, even in the past 2 weeks, to be completely honest with you, that I think are really going to change the way we think about the models we look for and how we look for them in the near future. And then we're going to define what magnons are and also talk about phonon excitations and why magnons are kind of the spin-dependent analog to phonons inside of materials. And then we'll talk about computing light dark matter magnon scattering rates. And we'll talk about this calculation in 2 different ways. We'll begin by talking about a first principles calculation, where we really use a detailed understanding of the target that we're scattering off of. And then we'll talk about how we can calibrate these scattering rates with neutron scattering data. So using actual data taken at the ISIS Muon neutron source to map out the response, to map out the single magnon response of the targets that we're interested in, and then mapping the neutron response to the light dark matter response of the targets. And then lastly, we're going to talk about axion absorption into magnons. So this is a dramatically different signal using similar targets. But the idea here is that we want to look for axions which can resonantly excite magnons. And then we want to be able to detect these single magnons, which is an important, outstanding question in this field right now. And at the very end of the talk, I'll briefly mention how you can use these recent developments in quantum magnetics to couple magnons to qubit systems. And then you can think about counting the qubit state or measuring the qubit state to be able to probe single magnon excitations inside of your target. Okay, so very briefly, we have a lot of evidence for dark matter. We know that it's 5 times more prevalent in the universe today than ordinary matter. And we also have evidence for its existence on a variety of cosmological and astrophysical length scales. And then there's a number of different ways that we can search for dark matter and try to probe its properties. We can, and this is usually drawn in this X diagram with dark matter particles, this kind of toy Feynman diagram with dark matter particles on one side, standard model particles on the other side, and going different directions in this diagram corresponds to different ways we probe dark matter. So for example, when we smash standard model particles together, that's what we do with colliders. 2 dark matter particles colliding in the center of the Milky Way produces photons, and that's indirect detection. And today we're mainly going to focus on direct detection, where we have the dark matter coming in, scattering off of a target in the laboratory, leaving, and then hopefully depositing some energy to the final standard model state that we're going to then read out. So the canonical direct detection experiment, I think, is based on nuclear recoil. And the idea is that that standard model state that we were just talking about in that Feynman diagram is a nucleus or a nuclei, a xenon or argon nuclei. And we build ton-scale tanks of these detectors, put them deep underground to avoid backgrounds, and then wait very carefully for a dark matter particle to come in and create electrons and scintillation light after scattering off the nuclei in the target. And these experiments have been going on for some time now, and they've the sensitivity of them has been dramatically increasing over the past 20 years. I think beyond a Moore's law rate, we've had improvements in the sensitivity, and the sensitivity that we usually parameterize as a cross-section versus dark matter mass. On the y-axis is how strongly the dark matter interacts with the nuclei, and on the x-axis is the dark matter mass. And you can see the current constraints by the LZ experiment, and these might not even be the most current because Xenon and Ton is also currently operating and putting out interesting results. But you can see that the current sensitivity that we have is very, very close to this neutrino floor where solar and atmospheric neutrinos act like a WIMP signal, and we don't expect to be able to reach cross-sections to search for dark matter which may interact via a cross-section that's deep inside of this neutrino floor, okay? And this, building this ultimate WIMP dark matter search, which reaches the neutrino floor, is a big part of it's a major initiative in the recent P5 report, right? So this is a major push in US particle physics to build a detector that reaches the neutrino floor. And one nice piece of other additional physics that you can do with this is that you can search for, the neutrinos don't necessarily have to be a background. You can actually look for the neutrinos and see them individually. And actually, this was recently demonstrated. This is the neutrino background from solar neutrinos, and Xenon and Ton actually found a few events consistent with this neutrino background, right? So there's interesting neutrino physics that you can do with these detectors in their next stage after they've already reached this neutrino floor. And then, of course, we see that these detectors are no longer sensitive to dark matter much lighter than the 10 GeV scale, and this is for kinematic reasons. If dark matter is much lighter than the nuclei you're scattering off of, you can't efficiently transfer energy to the system, and you can't put a keV worth of energy into the detector that can be detected, okay? And so all of these detectors, based on the nuclear recoil paradigm, fall off. Their sensitivity degrades rapidly for masses below the xenon and argon mass. And so one way to get around this is to use electron-based detectors. And one reason you might think that electrons are the way to go is because they're lighter, but that intuition would really work if we were talking about free electrons. What's interesting is that these targets are using electrons and silicon and germanium targets, and so the electrons sitting inside of these targets are not free. And the reason you can look for much lower masses is instead because the band gap of these targets goes down to the EV energy scale. And so the idea in this experiment is no longer you're kicking a free electron or making an electron recoil inside of the experiment. The idea is that the dark matter is coming in and taking an electron from the valence band, putting it to the conduction band, which then decays back down, or you drift over to a detector. And so there are many different experiments that are currently operating under this principle with silicon and germanium targets. The DOMIC collaboration, Sensei Super CDMS, and Edelweiss and CDEX. And this is a very interesting result that came out recently. And this was the DOMIC's most recent sensitivity to light mediators. So on the y-axis, again, we have the cross-section, but now we're thinking about interacting with electrons. And the model you should have in mind is a dark photon-like model, which has vector charges on the standard model side and the dark matter side, and the mediator is light. And for a long time in the light dark matter model building community, this freeze-in line, where the relic abundance of dark matter is set by the freeze-in mechanism, was kind of the gold standard, the benchmark model that we really wanted to search for. And it wasn't clear even a few years ago whether these same experiments could just increase their exposure to reach this freeze-in line, similar to how the sensitivity of the nuclear recoil experiments is improved by increasing exposure. However, amazingly, DOMIC was able to, they were able to understand their backgrounds, remove their backgrounds enough, and improve their exposure to be able to cover this freeze-in line. And so now the majority of parameter space for light dark matter, right in between the 1 MeV to GeV mass range, interacting via the simplest possible interactions is ruled out. So now,
is this still presuming some relation between the dark photon mass and dark matter mass?
yes, so this is assuming that the dark photon is very
3 times.
light. Huh?
3 times the dark matter mass.
No, so this is a light mediator, and that's given by the mediator form factor. Sometimes we parameterize this as a mediator form factor. So there's a similar plot for a heavy mediator.
Massless mediator.
Yeah, it doesn't have to be massless.
Yeah, but much smaller than the momentum exchange.
Exactly, right. As long as the propagator just has a 1/q² versus a 1/q² plus mv² in it, with v as your
But they
vector.
should also have a limit with heavy.
Yeah, exactly. And that's, they're very proud of this result as well. And that's the part I chopped off to make a comparison with the nuclear recoil results. And there they are actually probing the last little bit of the simplest possible freeze out dark matter model. So if you have some, I think it's scalar dark matter models with a scalar mediator, the freeze out predicted line was the highest of the benchmark models in terms of the cross section. And yes, the DOMIC results also exclude a lot of that parameter space as well. But these are kind of two different paradigms because they're being produced by dramatically different cosmological scenarios. And so now,
This is spin independent.
spin independent, right? And what I'm going to talk about today is trying to understand the spin dependent responses in, people also think about spin independent and spin dependent for nuclear recoil. We're going to think about spin dependent for electron interactions in this mass range and lower, which has kind of not really been focused on before.
So if we match the two plots,
Yeah.
it looks like there is a big gap between 1 and 10 GeV where the
Between 1 and, yeah. So this part of these masses are still not ruled out, right? And
because
so,
it's, no, but I was looking at the cross section
Mhm.
value, right? It's like several orders of magnitude that.
yeah. So
Between one
these
and-
are kind of sitting up over here. Yeah, these are so maybe way up.
And you
over
have,
here.
yeah, okay, good.
But these are still, let me say that, these are still much lower. So first of all,
But
there are some normalization factors. This is the reference cross-section to nuclei. This is the reference cross-section to electron. And so there's factors of ME and MN that
Yeah.
you should think about.
Right.
But these, this interaction is not going through a secondary process. And so this sensitivity is much stronger than, for example, Migdal searches. So people also think about exciting electrons via a secondary Migdal process in these nuclear recoil experiments. And that sensitivity, technically they do have sensitivity to lighter dark matter candidates, but it's way up here because you have to both shake the nuclei and then excite an electron. So it's kind of a second order process.
Okay,
Good,
thank you.
yes. Great, okay, so we talked a bit about how we can, good, so we can understand why the nuclear recoil sensitivity degrades due to kinematics, and we can also understand why this sensitivity degrades due to kinematics. The dark matter is too light to actually excite an electron above an EV scale band gap. And so
I
because
have another question. So
Yeah,
could you
absolutely.
show? I see. So the neutrino floor of fog varies a lot according to who represents it, because the gray area.
Yeah, exactly. If you're even talking about a neutrino fog, it's you're thinking about person-specific results for how much you can actually dig into this, right?
Yes.
This is just
No, not only that, the gray area seems to be represented to have different reach by different people. So then I'm seeing a plot here that goes almost until, so an order of magnitude below that.
Yeah, and that kind of depends on who you ask. This is more just for illustration right now.
Okay, well,
Good. Okay, so yeah, we can understand both the shut-off in sensitivity for these electron-based experiments and nuclear recoil-based experiments due to the kinematics. And so we can think about the kinematics in a target-independent way. So if we want to think about how to search for even lighter dark matter and use other targets, we should understand the kinematics of the process. And we would like to understand the kinematics of the process in a relatively target-independent way. And so if you just take the dark matter, if you only make assumptions about the dark matter comes in with some velocity v and then scatters and deposits some energy, so some momentum q and some energy omega q to the target, you can show that this energy, if you just take the difference in non-relativistic kinetic energies, ends up being q dot v minus this q squared over 2 m chi. And this is a statement about what energy can be deposited only based on the dark matter properties. It has nothing to do with the target properties. And then you can just maximize this function to demand that the energy deposited in a scattering event always has to be less than qv max minus q squared over 2 m chi squared. And on a log-log plot, this looks like these gray regions here. So we're showing the allowed kinematic range for different dark matter masses. So for example, dark matter with a mass of a GeV can deposit momentums up to an MeV and deposit energies up to a KeV. And that's what's shaded in this gray band here. Lighter dark matter is much more limited in the kinematic space that it can probe. And so you need different types of excitations, you need different kinds of targets, because you see that nuclear recoil with a keV or EV-ish threshold, you need very heavy dark matter to overlap where the experiment is sensitive to. And so you need very heavy dark matter. Again, for electron transitions with an EV energy, you need at least around 3 MeV of dark matter mass to get above this EV scale threshold. But single phonon excitations actually have energies between millielectron volt and 100 millielectron volt energy range. And so people have spent time thinking about how dark matter can interact with phonons. So phonons are collective excitations of lattice vibrations. And you should think about them as the modes that occur from a 3-dimensional harmonic oscillator system. So if you have many ions sitting inside of a lattice in equilibrium, approximately you can describe their potential, because they're all at rest, you can describe their potential as just a quadratic potential and it's harmonic. And the force constants of that potential are determined by the interatomic force constants that are binding these atoms together. And oscillations around that minimum define phonon modes. And here we're showing the energy of these phonon modes for a specific sapphire target. And on the x-axis, we have the momentum transfer and a bit more condensed matter notation. But there are a few important points that I want you to take away from this. The first is that there are very low energy modes here, and these are called acoustic phonons, right? And these are just sound waves. They have a linear dispersion relation at very low energies, and there are 3 of them. And then there's this forest of higher energy modes, all the way up to around 100 MeV, and this is very much dependent on the target. These energy scales are set by those interatomic force constants that are binding the atoms to the crystal. And so the idea here is that dark matter comes inside to the target and then generates a phonon, takes a no phonon state and transitions you to one of these single phonon states sitting somewhere in this band structure here. That's the general idea. And this idea has come a long way since it was first proposed. Now there are actual experiments being built. So this is part of one aspect of the tesseract collaboration and the tesseract experiment at Berkeley and LBNL, as known as SPICE. And the idea here is exactly based on the premise that I was just talking about. You have a very cold kilogram scale mass of sapphire or gallium arsenide, and then you put detectors on the surfaces of these targets and look for photons or phonons that are generated in the dark matter phonon scattering process. And again, because phonons have much lower energies than electrons, you can search for dark matter with much, much lower masses than you will ever be able to reach with electron-based transitions, right? And so if you want to cover this Friesen line below a dark matter mass of an MeV, you need to use phonons.
Do they have, are these experiments that actually, do they have actual reaches already?
Yeah, good. So the tesseract collaboration has 2, so there's no actual reach yet for this experiment. Tesseract has 2 different parts. There's SPICE and Herald. Herald is a liquid helium-based experiment, and they have that fabricated, and they have a paper that's been released about actually building it and cooling it down to the temperatures that they expect. And they're getting to that point with SPICE. So they don't have a sensitivity on here yet. We're very much in the early days of prototyping and trying to build these detectors and understanding backgrounds at the small exposure
It's
scale.
not known whether they can achieve this.
Yes, yeah, good. This is very much a projected sensitivity. If there are backgrounds present, right, at smaller exposures, this is going to raise this up. But there are also interesting ways you can make use of these targets to remove the backgrounds. For example, a lot of these targets are asymmetric. So the actual crystal structure itself is asymmetric. And so you can use the fact that the Earth is rotating through the dark matter wind to generate a daily modulation signal. And so you can use modulation on the day time scale versus annual modulation that people usually think about in the nuclear recoil context to also have another handle on beating down those backgrounds. So these are the games that people are trying to play. Good. And so what we're going to talk about today dominantly are Magnon excitations. And so Magnons are collective excitations of spin waves now. And so similar to how we thought of each of the ions sitting at the minimum of a potential, we are now thinking about each of the spins connected by inside of a magnet connected by some Heisenberg Hamiltonian. And so if you kick one spin that wants to push another spin inside of the target, and this is one illustration of a single Magnon mode going through a two-dimensional plane here. And what's interesting about this is that Magnons actually have similar kinematics as phonons. They have energies in the milli-electron volt to 100 milli-electron volt energy range. And they also have a similar description in terms of their band structure. There are acoustic Magnons, which have no energy at zero momentum. And then there's a whole forest of these optical Magnon modes that dark matter may also scatter to. And so why would you want to use Magnons, or why would you want to build a detector that is focused on reading out Magnon excitations versus phonon excitations? And I want to give you some intuition first before we go into actually how we're calculating these rates. And the intuition is for dark matter which interacts via that vector interaction Lagrangian that we were talking before, this is generally spin-independent coupling. So what you should be thinking about is essentially the dark matter is mediating some electric field to the target because it's coupling to the charges. The target now sees an electric field, and if the target is a polar material, so there are differently charged ions inside of the unit cell, the electric field that gets mediated is going to push the ions in different directions, and this is going to stretch that imaginary spring inside of the crystal, and now we're shaking ions, and shaking ions is exactly what phonons are, right? For Magnons, they're not going to be dominantly generated by electric fields. They're spins, and so they're dominantly going to be generated by magnetic fields. And so you want an interaction structure which is dominantly spin dependent. And so if you think about an interaction Lagrangian with gamma mu, gamma 5s, the point of this is that at low energies, this becomes a spin-spin interaction. So the dark matter spin interacts with the electron spin. And now you have something that's interacting with the electron spin and can now shake Magnons. And so just to give a brief example, if we focus on this, so this interaction Hamiltonian with gamma mu, gamma 5s is exactly what Carlos was talking about before. This is the standard SD spin-dependent interaction that is generally talked about in the context of nuclear recoil. This figure here shows the sensitivity to this specific model. So this high energy model is going to have a number of different interactions in the low energy limit. There are some interactions which are going to generate phonons, and there are some interactions which are going to generate magnons. And here is the sensitivity that you have to these couplings, a comparison between the phonon production and the magnon production. And you can see the main point here is that because the dominant interaction at low energies from this SD interaction Lagrangian is with spin, you dominantly generate magnons at and this is also in coupling. So the rate is a factor of 10 to the 4 higher for magnons at its peak at these light dark matter masses versus phonons. And so there is a real tangible benefit for matching not only the kinematics of your target, but also the interactions and the type of excitation the target has to the type of dark matter signal that you're looking for, right?
Well, what's the sensitivity in terms of a similar number for the spin independent?
For the spin, yeah. So for the spin independent, it would look flipped, right? Because even in the spin independent interaction, right, you still have terms like at higher order, you have in the non-relativistic limit at higher order, you have Pauli spin interactions.
What's the limit on those couplings?
What's the limit on those couplings?
Or sensitivity on the?
Oh, in terms of couplings, that's a great question. I'd have to go back and convert the cross section, the reference cross section. So it's completely degenerate with what I was showing you earlier here, right? So you can take this, and this sigma E is just a function of the couplings, and there's ratios of masses. So I think again, and this is also normalized to ratios of the dark matter mass and the mediator mass, so it's a bit hard to compare overall. Generally, I think those couplings for cross sections in the 10 to the minus 40 and below range are G's. When written in terms of the couplings are 10 to the minus 12, 10 to the minus 14, very small. I mean, these are that's generally the combination of couplings that you need for the Friesen abundance. So it could be even smaller than that, the smallest cross section that I was talking about. But yes, very, very small couplings. Okay, so that was just an example, and this is one calculation that we've performed. And again, this is just kind of an appetizer calculation. Now we want to actually calculate or discuss how we actually calculate the rate. How do we get the sensitivity, the projected sensitivity that we were showing before? We need to be able to understand, at a very detailed level, how many magnons are created when dark matter scatters off the target. And we're going to go over two different types of calculations, a first principles calculation that was done a few years ago, and then a data-driven calculation that me and my collaborators have been working on recently.
Do you agree?
Well, let's stay tuned. You'll see soon enough, but the answer is yes. Otherwise, I'd talk about something else. Good, so I think the idea of the calculation is pretty similar, or is pretty easy to understand, especially if you don't want to worry about screening effects or higher order effects. Really, what we're doing at the end of the day is computing, what we want to do is compute Fermi's golden rule, right? We want to start in a system, a very cold system that has no Magnon excitations. And we want to be able to understand the scattering rate to a single Magnon mode. Those nu is the branch index, and so that counts the branches in the band structure that we were talking about before. And K is the momentum in the first Brion zone, right? So these are just the quantum numbers of the actual Magnon state of the system. And now we need an interaction Hamiltonian that actually generates this transition, right? We want to quantum mechanically compute this. And what this interaction Hamiltonian looks like, right, is generally something that depends on the sum of all of the spins inside of the target. So you can imagine O chi here as coming from the high energy theory. For example, in the SD case, this O chi might be related to the spin of dark matter. In other models, it might be the momentum of dark matter that gets dotted into the electron spin. And here L is an index for each of the unit cells, and then J indexes the ions inside of each unit cell. But you can kind of lump LJ together as just summing over each of the magnetic ions inside of your lattice. The dark matter is going to interact with each one of them in a certain way. And this S is what ends up being quantized in terms of Magnon modes, right? And so now we actually need to be able to write this spin operator in terms of Magnons, because we want to be able to commute this A dagger through the A daggers that are sitting inside of this S operator, right? And so now this is, in some sense, all the particle physics right now. Now we need to understand the condensed matter physics of this. And as I was talking about before, we can think about the target Hamiltonian as just some Heisenberg Hamiltonian. And so we have the spins on each of the sites are coupled by some exchange matrix J. And what's nice about this J is that, yes, you can get it from first principles, density functional theory calculations, but you can also fit it to neutron scattering data. And so there's a lot of people in the neutron scattering community, which essentially, as we'll talk about more later, they scatter a neutron off of a target, they measure the response, and then they're able to predict, essentially doing a similar calculation to what we're doing here, predict the response in terms of the J's, and then fit the J's to neutron scattering data. But once you have these numbers, your target Hamiltonian is defined, and now you can quantize it. And the quantization is a fun little calculation, but you have to go through this multiple steps, Holstein-Primakov transformation, and other fun quantum mechanics. But at the end of the day, right, what we're doing is very analogous to the harmonic oscillator, where initially we have a Hamiltonian in terms of some physical operators, and we want to turn that into a Hamiltonian in terms of the operators that quantize the actual system. And so those details are sitting inside of these polarization vectors, essentially, for each of the magnons. Good, okay, so you can go through the calculation to understand the sensitivity. And again, we're showing the cross section on the y-axis for a kilogram meter exposure and no backgrounds. And on the x-axis is the dark matter mass. And so a few salient features for all of these different models. The first is that at very low masses, we again see a fall off in the sensitivity. And that's really due to the threshold of these experiments, and which we want to be at the milli-electron volt level in order to actually see the magnons that are produced, right? And so the different numbers here are for different threshold values. As you increase the threshold, you're losing out on scattering two different Magnon modes. And so the sensitivity is decreased. And then, again, we have a magnetic dipole model that we haven't talked about yet, but we'll talk about soon, an antipole dark matter model where we have an antipole coupling on the dark matter side and a vector coupling on the standard model side, and then a pseudo-mediated dark matter model, which it has to be a subcomponent of the dark matter. And the idea here is that you have a fermion with a scalar mediator and it couples with a gamma 5 on the electron side, right? So you need a gamma 5 somewhere, even in the scalar case, to generate these spin-dependent responses, generate these spin-independent interactions. And all of these calculations were performed for a yttrium iron garnet target. And this is the target that it's very popular in this magnonics community because it's very well studied. It has very high quality phonon modes. They have a very long lifetime relative to the magnon modes, in other systems. And so how you would actually implement this and reach and achieve the sensitivity, right, is you want to do something similar to the SPICE proposal where you have a kilogram of YIG at a very cold temperature. And then the important question becomes, how do you actually read out these magnons? How do you read out single magnons? The single phonon readout mechanism has been well studied, and that's understood that you can kick a phonon into a transition edge sensor and then it breaks Cooper pairs on the surface. But actually what happens when you have a YIG target is uncertain. And it's not even certain that these transition edge sensors will work inside of the magnetic field, right? Remember, this is really a magnet, right? So this is some magnetic field associated with it. And a lot of these superconducting components don't work well inside of a magnetic field. And so this is a challenge. And at the end of the talk, I'm going to talk about one way, potentially, we may be able to solve this problem of doing single magnon detection.
Do you have a case where the vector we have vector mediator that couples to shoot vector current in the dark sector and a vector current in the standard sector?
We did not look at that.
Huh.
That's another, these are just 3 candidate models. I don't have, I think there were, when we were picking these models, there were other bounds that we had to consider. And so we went through the list of simplest models. And there were reasons. I can't construct them right now, but I can get back to you about why we didn't look at some of the simplest models. But you're absolutely right that those dimension 4 operators can also generate a spin-dependent response because you have extra gamma 5s on either side.
Yeah.
But you need the gamma 5 on the electron side to dominantly get the spin coupling to the electrons. Because you can look for that other interaction where you have a gamma 5 on the dark matter side, but that's going to involve a spin of the dark matter. But that will still generate phonons. And so that is a model that you'd actually want to use a phonon target for that reason. Yeah. Good. Okay, so YIG is not the only target that you can use. This is not my work, but this is other people's work in the community, and they studied the response of this nickel oxide target. This is an interesting target because it's an antiferromagnet. And so one of the problems that we were just talking about in terms of detection for the YIG target was that you don't actually know if your TESs work inside of an external magnetic field. But of course, one nice thing about an antiferromagnet is that it doesn't actually have any large magnetic field coming out of it. And so you may be able to attach some of these detectors. And so this is the sensitivity for a number of these different antiferromagnetic targets. And this paper also interestingly understood the 2-magnon response. So there's part of that kinematic regime where you no longer have enough momentum deposited to excite a single magnon, and all you can do is excite 2 magnons. And this paper used an effective field theory description of the magnon dark matter interaction to understand that 2-magnon process. So essentially to set up an interaction Hamiltonian, which now has 2 spin operators in it. And then at the very lowest masses, this is what's dominating the sensitivity.
Why the 2-magnon has lower energy?
Because when the 1-magnon is available, that's the leading order process. You can kind of think about this 2-magnon contribution as coming from an anharmonic expansion. So the leading order expansion in the interaction is 1 spin operator, and then you have one with 2 spin operators.
But you imply that this has a lower energy.
Yeah, yes, good. So the idea is if you have some, let me see if I can. So here we're only talking about acoustic magnons. So this is zero momentum, and then this is the energy. And say you have some energy threshold, and say you have a scattering process, which maybe gives negative momentum just for illustration. And so you have enough energy to excite Magnon modes, but you can't excite one Magnon mode that you'll see because this is the threshold of your experiment. And so to match kinematics, you need the dark matter kinematics to overlap the Magnon kinematics above the threshold, right? And so that's what's happening, for example, in a single Magnon scattering event, you're getting this process. But for something like this, you aren't actually generating a measurable Magnon, and so you have to use a 2-Magnon process at the lowest energies. And so then the idea is you're making this happen, and you can still conserve momentum and energy by making 2 Magnons. And that's why you need to do that. So at lower thresholds, the 2-Magnon dominance would be much, much lower. Okay. And again, this is the magnetic dipole interaction, and we're still parameterizing Bragg cross-section. And apologies for the confusion, but people like to use different conventions for the figures. And so this is a different target. This is a quasi 2D material that some people at Berkeley recently studied. And again, we have the sensitivity, but now we're showing this in terms of a dark magnetic dipole moment versus the actual couplings or cross-section interactions. And this target is interesting, not because of the raw sensitivity that it has. Generally, when you're thinking about quasi 2D materials, what you want is you want to pack as many targets into your experiment as possible, right? You want as many electrons, the highest electron spin density possible to maximize the scattering, right? However, what this quasi 2D material does award you is this daily modulation. So because there's an anisotropy in the band structure here as a function of momentum, now the dark matter sees a different Magnon that it wants to excite at a different time of the day. And the idea here is that if you orient your experiment in the z direction at some time of the day, misaligned from the incoming dark matter wind as we're moving through the Milky Way, as the Earth rotates throughout the day, the z-axis of the experiment is going to see the dark matter wind at different directions, and the rate ends up being dependent on that inner product to some degree, and that actually gives you some amount of daily modulation. And so you can see that for this quasi 2D material target, you're getting daily modulation on the order of 10%. And so that only reduces your sensitivity here by a couple orders of magnitude.
Why does it change in phase when you raise?
Why does it change? Yeah, good. So these plots are always interesting because they vary in a very detailed way. They depend on the exact band structure, right? And so here at low masses, you're getting a very nice smooth function that's very similar, probably because you're at the very lowest dark matter masses and you're only probing those acoustic modes. At higher masses, you're actually probing the acoustic modes at higher energies. And what actually happens out here is that the acoustic magnons are not exactly linear. They tend to taper off and they flatten out similar to phonons. And so you get an interesting structure at the edges, and that can change the modulation rate for these heavy masses. Good. Okay, so those were some example models. If you want to understand how any dark matter model can interact with magnons in your system, you need to use effective field theory. And so that is what we did in this work in 2020. And the idea is, again, at the end of the day, we're just calculating Fermi's golden rule, but now we're calculating it with all of the bells and whistles involved. So this is the scattering matrix element. The scattering matrix element, again, depends on the 0 to single Magnon transition matrix element of the electron spins in the system. And then this F, this coupling coefficient, depends on the high energy theory. And then you can explicitly go through all the high energy theories and find how these couplings, these C couplings, depend on the high energy theory. And that's been done in this work. But this line of reasoning and this calculation is very similar to the effective field theories that people are also thinking of for the nuclear recoil calculations. And there, the idea is that you understand the sensitivity. The idea there is that if you can understand the experimental sensitivity to all of these coefficients, then for any dark matter model, you can map the sensitivity to those parameters back onto the sensitivity of these coupling coefficients, right? And so from a first principles level, we have a very good understanding of how to calculate the Magnon excitation rate in any target, for any material and for any dark matter model. Okay, and now we're going to talk about the data-driven approach, which we've been working on now. And so if you want to understand the dark matter scattering rate, you need whatever particle you're scattering through, you would want it to have similar interactions to the dark matter that you're looking for. And this is where a dark magnetic dipole moment model is very beneficial, because you immediately see the comparison with the effective interaction Lagrangian for a neutron where it has a magnetic dipole moment, right? You would expect to just be able to understand the scattering rate for a neutron based on the first operator, and then rescale that scattering rate to the dark matter model that you're interested in down here, right? And so you need the interaction structure to be similar. You also need the kinematics to be similar too. And so what's nice about neutrons, right, is that neutrons have around a GeV of mass. And if they were moving as fast as dark matter is moving, right, we know exactly the kinematic space that neutrons can impart inside of your detector, because that's exactly the same as dark matter kinematics at a mass of a GeV. And so that is shown here, again, going back to this kinematics plot. And so if the neutrons were being fired at 10⁻³ C, all of this, you would be able to understand the single Magnon response of your target in this whole kinematic regime, and then therefore also be able to recalculate the dark matter sensitivity for much lighter masses, because you know how the target responds over all of these omega and q's, right? And so that is that's the dream in some sense of using neutron scattering. That's really the end goal. Good. And so how do we think about the data itself? Well, the data itself is sometimes parameterized in terms of what's known as a dynamic structure factor, which is just a rescaling of the neutron scattering cross-section. So this is the neutron scattering cross-section for the final solid angle and energy deposited. And then this quantity Sn is directly measurable. And again, for that magnetic dipole dark matter model, we see that we can directly write the excitation rate in terms of this measurable quantity, in terms of this dynamic structure factor. And then there's also kinematics hiding inside of here, and this tells you what part of that kinematic plane you should be integrating over and with what weight, right? But really, the physics of kinematics and the halo mass, or the halo velocity distribution, is all sitting inside of this G function. And then the measurable data is all sitting inside of Sn. And then there's fun normalization factors that you have to ask neutron scattering experimentalists about. This NF is the number of formula units of yttrium iron garnet inside of the unit cell, and that's actually a factor of 8. So you gotta talk to your friends about this. And so what we did is we went and asked experimentalists for this data, and this data they collected for the YIG sample that we care about, and they collected this to be able to understand the band structure of YIG. But they took data at a variety of Qs and omegas, and this is actually one of the experiments. This is the MAP spectrometer at the ISIS neutron at Muon source. And the idea is that you shoot neutrons, you chop a beam of neutrons that are slowed by some water in between, and you chop this pulse beam of neutrons, and then you actually just set up detectors at different angles outside of the target, and then you scatter neutrons and you actually measure the counts that are sitting inside of these detectors at different angles. And you use that time of flight information, the calorimetry information from the amount of energy deposited in the detector and the time it takes to actually get there and the angles. You use all of that information to reconstruct the kinematics of the event that occurred. The kinematics of the event that occurred are the Q vector and omega that were deposited to the target. And one way to visualize that information in a 2D slice, because it's a 4-dimensional parameter space, is shown here. And actually a lot of the features of the detector can be reproduced from this figure by following around certain angles. But these are actually the counts for a given Q and omega, or for a given Q, X, Q, Y, Q, Z, for a given energy deposit, right? And so it was pretty fun to actually be able to reproduce. We actually made this plot, Kevin made this plot first, and then was able to work backwards what the detector should look like. And then we went inside of some old paper that actually had a picture of the detector, and it matched up, right? So we actually kind of detectived our way back to what the detector should look like, which was
what are the cubes
pretty
in
exciting.
front of the person?
Huh?
The detectors are which ones? Are the...
Yeah. So these are the detectors, and so there's a high angle section and
those cubes in front of the guy.
Yeah.
What are those?
Just calorimeters. I don't know the details of them. As a theorist, they're counters, right? If a neutron comes through, they tell me yes, or they tell me no, but they have very good angular resolution. And so this is actually pretty smeared out. They not only rotate the sample to access different parts of the kinematic space. And yeah, so some of these zero counts are actually telling you that the detector, the scattering rate is not very high, right? Okay. So you can understand this in a different way. Again, we can go back to, we're gonna focus on this kinematic coverage figure. And we're really focusing on dark matter masses between 3 MeV and 100 keV. And I said before that if the neutron was moving at 10⁻³ you'd get all of the kinematic space that you want. However, the neutrons are more at room temperature. And so their velocity is much, much smaller, around 10⁻⁵. And so that lowers this top edge here, which really is approximately the momentum times the velocity. And so the actual data does not go to as high energy as you might think for a neutron. And the data is only available in this part of the kinematic regime. And so we have to do some amount of extrapolation to understand the dynamic structure factor outside of that regime, but we're doing it in a way that's based on the data that's directly available to us, right? And then we calculate the rate by integrating over the phase space for certain dark matter masses. And so what you find is a good agreement between this data-driven approach and that first principles Heisenberg model. Again, here we have the magnetic dipole model with the couplings on the y-axis. Excuse me. And the dark matter mass on the x-axis. And so there are actually two points of future work that we want to understand. Here, it turns out at very high masses, both the data-driven approach and the first principles approach are a bit of an overestimate. And the first principles approach is a bit of an overestimate because we didn't take into account the magnetic form factors. The electrons are not point-like particles sitting on each ion. They're spread out to some degree, and when you transfer enough momentum to resolve the electron wave function on each lattice site, there's a form factor involved with that. And so that's going to reduce the sensitivity of the first principles calculation. And then also the data-driven approach is actually picking up some phonon contribution as well. So that's enhancing the rate at very high Q. But overall, at a first pass, this level of connection between the data-driven approach and first principles is very promising. Okay, and then you can also recast other dark matter models. I'm going to move on and move to absorption.
Yeah, the agreement looks too good. Right?
Too good. We spent a long time thinking about how good this is.
Very good.
But yes, we're very happy with this. Good. So the rate can also be written in terms of the magnetic susceptibility, and you can understand the response from all of these different kinds of dark matter models by collecting and reparameterizing their interaction coefficients in terms of a form factor, and that form factor then gets dotted into the two-dimensional susceptibility when you calculate the rate. And there's some interesting physics associated with what information you can actually extract just from neutron scattering versus what you would want for more general dark matter interactions outside of the magnetic dipole model. Okay, and so now we're going to talk about absorption into magnons, which is a dramatically different kinematic regime. Instead of scattering, instead of the energy deposited to the target being much less than the momentum transferred, now we're in a regime where the energy deposited is much, much greater than the momentum transferred. And we're thinking about almost perfectly vertical transitions in the phase space. And so our main target that we're going to be thinking about is a derivatively coupled axion. And so there have been many attempts to search for that axion interaction, this electron-coupled derivative interaction. And at high masses, this interaction can just kick electrons from a valence band to a conduction band, or just excite an electron inside of a xenon or an argon atom. And so all of those detectors have sensitivity to axion masses heavier than an EV. However, for axion masses much less than an EV, there are no current experiments that can get below stellar cooling bounds for the axion electron coupling, which is kind of surprising. This plot obviously looks very different when you think about the axion photon coupling. But for the axion electron coupling, you can't use haloscopes because dominantly you're interacting with electrons versus photons. And so you need to think about new ways to search for axion dark matter coupled to electrons in this very light part of parameter space. And so how do we understand the physical effects of that derivatively coupled axion? Well, there's two different types of interactions. There's the axioelectric interaction, which is coming from the time derivative, and that is dominantly what's causing the excitations at very high masses. But at very low axion masses, the dominant term ends up being the axion wind term. And you can understand this because this A dot almost gives you an extra suppression of MA over ME. So for axion masses closer to the electron mass, the axioelectric term is going to be dominant. For lighter axion masses, the axion wind term is going to be dominant. And the phenomenology of the wind term, call it the wind term because it effectively is an external magnetic field that's aligned with the axion velocity. So this is just a B dot S interaction Hamiltonian, and the effective magnetic field goes as the gradient of the axion field. Okay, and so we have our high energy Lagrangian. We take it down to its non-relativistic limit to understand how it interacts with the spins in the system. We get some interaction Hamiltonian, and now this interaction Hamiltonian, right, tells us that we can convert an axion to a magnon resonantly. And we have many magnon modes, and so we would expect to be able to absorb axions onto any of those magnon modes. And this is very similar to Caspar wind. So there you're looking at NMR, and you're looking at nuclei spin precessing. Here, essentially, we're looking at electron spins precessing inside of a solid target versus the target we're using for Caspar. So again, you want to go through Fermi's golden rule, and now we're going from a state which has an axion to a state which has a magnon. And curiously enough, what you actually find is that the rate is 0 in the simplest possible targets, and that's because there ends up being a selection rule. If you couple to all of the spins in exactly the same way, that total operator actually commutes with the target Hamiltonian, and that creates one of these selection rules. And you need to find ways around the selection rule by playing with your target Hamiltonian, or using external magnetic fields. And so for example, an external magnetic field essentially lifts the band structure for all of the modes and allows you to absorb onto the lowest magnon mode. And you can also use anisotropic exchange interactions, which break some of the degeneracy that you have for the selection rules. And so weirder targets and external fields are what you need to be able to look at absorption of axions into magnons. And again, you can also do a first principles calculation, and you can use a data-driven approach where you take the measured data at the zero momentum, take the measured data in the zero momentum limit, and you can write this in terms of the permeability instead of the susceptibility, if you would like.
Anisotropic exchange interactions are a property of some materials? Or?
Yes, yeah. So that was what I just showed here. So for example, you can find in this paper specifically, they just give you the fit exchange parameters. They make some measurements of the system. They estimate what these exchange parameters
they have
are.
some pattern or some regular pattern in spite of the anisotropy.
Yeah, exactly. And there are also other terms you can add here, but they're very good at cooking up these weird systems. But you can go back to YIG, like we were talking about, and on the y-axis we have the axion electron coupling, and on the x-axis we have the axion mass. And so for example, if you put the yttrium iron garnet target inside of a Tesla magnetic field, that shifts the resonance to around 120 micro eV, which sits here, and you can absorb axions at a rate with the couplings given by some of the popular QCD axion models. You can absorb axions at a kilogram year rate and may be able to detect a QCD axion via its conversion into a magnon. Okay, and then these are example other targets. So this is that anisotropic target. You can have magnon modes at higher frequencies, and you don't need an external magnetic field because you've broken those selection rules in other ways. And then you can also get around the selection rules with these other potential targets. Other people in the community have thought about their favorite magnetic target. Again, in an antiferromagnet magnet, you can play these same games, and this nickel oxide also has some anisotropic exchange interaction, and you have two peaks inside of the single magnon response, and then you also have similar concerns about, or you can also play a similar kinematic game to get two magnons out of this absorption, where instead of just exciting onto one lowest mode, you actually excite two magnon modes, and there's some sensitivity up here. Okay, so all of this has kind of been under the assumption that you can detect single magnons, but that is a hard thing to do. One way in which we're thinking about possibly doing this is to couple these magnons to qubit systems, because we're getting very good at actually counting qubit states. And so for example, the idea is that if you have a magnon inside of a small sphere of magnetic material, and you couple that to a qubit, the magnon is going, if there is some coupling between these two systems, the magnon is going to Rabi flop over to the qubit and take the qubit from its ground state to its excited state. And then you can just ask the qubit, are you in an excited state? And that is essentially single magnon counting, right? And this is fantastic for the axion masses that we were talking about before, because the axion masses generally correspond to gigahertz frequencies and above when you do that conversion. And this is where qubit systems dominantly operate today in the 4 to 8 gigahertz range for normal transmon qubits. And so this idea to use a qubit coupled to a magnon, and this is known as quantum magnonics, this was recently funded under Quantize 2.0, and we're hoping to use these detectors we want to first understand their sensitivity to axion dark matter, and then we want to understand if a dark matter that comes in and scatters can excite high energy magnons that then down convert to lower energy magnons. And this is a very similar idea to what we thought about in the phonon context. So this is not quantum magnonics, but a quantum acoustics proposal to now have a phonon in a certain system that's kinematically matched to a qubit. The phonon swaps with the qubit, so you can do single phonon counting. And the hope there is that instead of a new physics signal dominantly interacting the phonon that's coupled to the qubit, you dominantly make some other phonon inside of the target, which may be a relatively big target, maybe the kilogram scale that you would like, and then it should down convert and shower into the phonons that are kinematically matched with the qubit, and then you can just count them. And so this is potentially a low threshold single phonon counter, and the same idea here we think can be applied to magnons as well. So we're excited to explore that. So
what is the qubit?
what is the qubit? So good. This qubit for the magnon, so in this case, for the phonons, these E fields are coupled to a charge qubit, a transmon qubit. In this case, we need to use a special qubit. This is an electron on neon qubit. So the idea is that the electron is sitting in, there's some potential that binds an electron to the surface of solid neon. And the lowest two states of that system create a qubit. And you need this system specifically because it can operate inside of an external magnetic field. Right? You want to be able to scan axion masses. You want the whole system to work inside of an external magnetic field. And so what's interesting about this is that this is actually almost the perfect use case for this type of qubit.
Magnon qubit interaction is very efficient.
Yeah, you can design these this superconducting resonator to get a coupling to count single magnons, and that's been demonstrated. And they've also coupled magnons in different Higgs spheres via these resonators as well. And one nice thing about using, so this was all the other haloscopes that are searching in this part of parameter space had similar detection ideas, but there they were matching the magnon frequency to a cavity. And the problem with that is that you can't scale that, because if you want to go to high masses, you have to have a very small cavity. Here, you can very easily scale the system because you have these planar superconducting circuits connecting the Higgs sphere and the qubit. And these are very small tiles, essentially. And then you can just tile these setups up into these wafers and put them into dilution refrigerant.
How many qubits you need
what ends up being more important, interestingly enough, is the mass of the Higgs sphere. You scale much faster with the mass of the sphere inside of each of these tiles than you do with the number of tiles. If you're reading them out each incoherently, if you're doing counting incoherently between them. But you can get order hundreds, right? And you can get more qubits than you need for quantum computing because you don't need these to be entangled. We're not using any special properties of the qubit here. Really, this is our way to count magnons, right? That's why we want to use them. And so we don't need to have entanglement across 100 qubits for a very long time, which is what you dominantly want to be doing with these systems in other technological purposes.
You can scale up, so it doesn't need a lot of them.
Yeah. So these are very small. So you can with a total of like a gram of material, you can kind of get to stellar cooling bounds. If you just Yeah, so these are generally like milligram size right now, but there's really no reason you can't buy bigger Higgs spheres. And then you can put 1,000 of these inside, inside of a few wafers inside of a fridge. That's the idea. Good. Okay, so that brings me to the summary. Magnons are exceptionally sensitive to specifically spin-dependent light dark matter models. Neutron scattering data gives us a new way to understand in a data-driven way the response of these targets to many different types of dark matter models. And quantum magnonics provides an approach for doing single magnon counting, which can push past SQL limited readout techniques at very low frequencies. Thank you. Other questions?
So where are these experiments located?
So for this system, this is a collaboration with Argonne and Notre Dame, and the fridge is going to be at Argonne, but then the qubit itself was developed by people at Notre Dame. So the actual qubits are at Notre Dame. A lot of the fabrication and multiplexing expertise is at Argonne. And then there's a couple of other miscellaneous theorists involved in the project, like myself.
But you're part of it. So who is at
Yes.
Argonne?
Gensheng Wang is the lead
Okay.
PI, but
Okay.
Clarence and Yi Li,
I see.
Valentine Novosan, because
Yeah.
you know these people, so I can tell you the names.
Okay, very good.
Maybe I can also ask
Yeah,
a
absolutely.
question. Maybe it's a little naive. Just generally, what influences the choice of the material you use? Is it just a band gap?
Yeah, good. That really depends on the dark matter model you want to look for, right? If you want to look for dark matter with heavier masses, you don't need a very small threshold. If you want to look for very light dark matter, then you need targets with very low energy excitations. You need a very low threshold experiment. And now that's one axis that I think has been well appreciated. Now we're focused on a different axis, on an interaction axis. You can actually use different types of excitations and targets and match the interaction and the kinematics to enhance sensitivity. So because you want a target with spins, if your dominant interaction term is spin dependent, right? It's generally the idea.
Explain in a little bit more detail how the transform qubits couple to the magnets.
Yeah, good. So these aren't transmons. This is, again, qubit is a two-state system.
Yeah.
And the lowest two states of this electron
Sorry, what kind
are
of
the
qubit?
qubit system. They're called electron on neon qubits because the electron is sitting on a solid neon surface. These are
Is it
like
based
new.
on superconductivity or like does it have anything to do with the superconducting qubit?
Yeah, so these resonators that you're coupling to are generally superconductors. So these are like waveguides, and so you can kind of think of this as a cavity in between connecting both of those. And so the idea is that the changing B field creates an electric field, which creates mode inside of this superconducting resonator, and then that electric field mode can interact with the electron inside of, that's sitting on the neon surface inside of the qubit. But yeah, so both of these systems have been independently built and tested. It's a question of really getting the masses that you need for the Higgs spheres, scaling everything up, and then also understanding how you can mitigate the dark counts, especially because they're getting better at reading out these individual qubits, but not at a level that needs to be improved. And so that's definitely one area of improvement. So they call this like a single shot fidelity, and that's how often you actually get the state right in this, or how often, for example, if it isn't a one state, how often you measure it to be in a one state. That's the fidelity. You want the fidelity to be high. And generally they're shooting at the 99% level right now. And there's reason to think that that can go even higher because other components of the system operate at a higher fidelity. And so the limiting components today are generally operating at a 99% fidelity. And that ends up, again, not being the dominant, it's an important factor in the sensitivity calculation, but it's not the dominant factor. Again, really just maximizing your exposure and just getting bigger gig spheres is where you really win in sensitivity.
How big is one qubit?
How big is the qubit? I don't know. It's small. So this is 100 micrometers because this is around a milligram size sphere. And so, you know, this is all fitting on one tile. This is a millimeter, right? So hundreds of micrometers to a millimeter. Very, very, very tiny, right? So you can scale them up. More questions?
There are no more questions. Let's thank our speaker.
Thanks for joining, Asher.
Great talk.
Oh, I shall.
Make sure that's in the record.
Nice to get positive feedback from someone, you know.